So resolution is already what's up? Oh my
Let's get started. It seems like the numbers are a bit smaller. That entire row has vanished. I guess people will show up in a minute or two, or maybe quiz 0 has scared off people. So that's a good segue about some announcements. I'll be bringing this up at the end of the class as well for people who are coming in late. But a couple of things were raised, a couple of questions were raised at the end of the last lecture. I just wanted to cover that about logistics. This class, as you probably are aware, is a mix of grad and undergrad students. And some people came to me and said, is there any difference? So people who are taking this class, who are in this class for 5350, the undergraduate class, will have to do a little bit less work. Namely, your homeworks will have, grad students may have to do extra questions in homeworks or possibly extra questions in the exams, or maybe more difficult questions, something like that. There will be some extra work in the homeworks and the exams for graduate students. And grad students and undergrad students will be curved differently. Any questions? Yes?
On Canvas, myself and some other undergrads show up as the...
Yeah, right. So everyone on Canvas shows up under 6350. That's mostly for my convenience, so that I don't have to post an announcement 3 times. But you are in whatever you are registered for. Canvas does not let, I don't know, Canvas does things. It has a mind of its own. Okay, any other questions? Another thing that came up was, I had a slide on the collaborations and cheating in the last lecture, and forgot to mention a point. Those of you who are not in the School of Computing, the School of Computing requires you at some point to sign the policy on misconduct. You can find it on the class information page. You can just sign it and return it to the front desk. The point, if you've done it before, you don't have to do it again. If you've never done it before, then you need to, mostly to, basically it's a statement that says that you agree with the policies of the department. Okay? If you want more information, look it up on the class website under the information section. Just reminders about the survey and the quiz. I see that many of you already attempted it or finished it. Thank you. If you've not, please give us information on the survey. And well, the quiz is not by choice, you have to. And again, it's nothing to be worried about, or it's supposed to be asking questions that you should be familiar with, or mostly it's a means that allows you, think of it as a mechanism that forces you to go back and read the stuff that you may have probably seen 3-4 decades back. Oh, you're laughing now. The survey is very useful for us, mostly to help us design the class for you. One of the most important parts of the survey, in my opinion, is which languages are you, programming languages, are you familiar with? We've been thinking that we are going to restrict the list of languages that we'll allow for the assignments, for the programming parts of the assignments. And most likely what will happen is we'll take the top, most frequent 4 or 5 languages that are listed. So if you believe that there is a language that only you and only you will use, please mention it in that survey, because otherwise you might not end up using that language. So far, like, we've got a few responses, I mean not few actually, about maybe 40% of you responded, and so far it seems like the most dominant languages are Java, MATLAB, something in the C family, right? C, C++,
Python.
and Python. If you think that there's a language that's not in these four that you need to use, will use, and only in your life, you should do it and return it to the front desk and fill out the survey, finish the quiz. Alright, so let's continue from where we left off, or what we saw in the last lecture. The last lecture we just looked very broadly at a definition of learning. And the main take-home message from the last lecture was learning is generalization. If you do not generalize, then you are not learning. If you can, because otherwise, that's the difference between learning and remembering. Remembering is just putting things in a database and retrieving it. Learning is generalizing to previously unseen situations or examples or instances. And we looked at the badges game. Let me just remind you what the badges game was. And today we'll be looking a little bit more at badges game, and we'll start formalizing the supervised learning set. So let's go back to the badges game just to bring it back to memory. The game was that you have to predict a plus or a minus based on this label, or based on the name. And I told you that there was more data on the class website and encouraged you to go take a look. Did anyone do that? Yes?
Yeah, I looked at it.
Okay, and did you come up with?
Okay, I concluded it's not based on the number of A's, it's not based on the length of the first name being longer than the last name or vice versa, it's not based on the female plus total number of letters being less than a threshold, it's not based on...
So you came up with a lot of things it's not.
Yes.
Okay, and anyone come up with a thing that it is, or it might be. Okay.
Second letter is a vowel or consonant.
Excellent. Let me just repeat that. This function is the plus, the label is a plus if the second letter is a vowel. The label is a minus if the second letter is a consonant. And it's kind of, you were on the right path. You were basically listing functions, and what you did is actually an important thing to remember, because learning is really search over functions and rejecting things that it's not. It's not whatever, all those things that you said. Now, the question that you have is, okay, once you've done this, once you know that this function is the second letter, blah, 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 you can label names that you've never seen before. What you've done in that process is, by generalizing to this function, you can go and classify instances that have never been seen before. And that's the point of learning. So, that's right, the second letter, just to repeat, if the second letter of the first name is a vowel, then label it as a plus, otherwise label it as a minus. That's the function. This is kind of a silly game, there's nothing much hinging on this, but it has a lot of useful characteristics that we will be looking at. We'll probably be looking at this data multiple times. The question is, how do you know you're right? How did you know that you were right?
Let's go to the list and test your...
Yeah, but how do you know those are all the names that exist? Maybe I'll give you, let's say, I don't know how big the data set was, about 1,000 or something. Did you test all of them?
In the data set, yeah.
Okay, so you probably wrote code for that. Or not, I don't care. The point is, let's say there are 1,000 names that fit that function. How do you know you're right? What if, after that, I come to you and say there's another name where the function doesn't fit? And now you're back to the, do you see that such a situation can happen? I could be adversarial, and every time you pick a function that fits some subset, I'll change the function and make it a function that does not agree with what you have. I could do that. So a question that I want you to think about, not necessarily answer right now, is how do you know you're right? And this is actually very important. How do you know that you're right? And we need to formally quantify that, and we will be asking that question more formally as this semester goes on. Another question, did anyone else come to the same function by the way? A few. So let me not pick on you again, let me ask another person. So how did you come to this function?
I don't really have a good explanation for it. I just looked at it and
It jumped
guessed
out.
and checked and
Okay.
saw that one.
And how about you?
Same.
Same thing. So you guessed and checked. And is that the same for you? Okay. And you did the same thing, but you did not guess and I won. But in some sense, what you guys did was search. You searched over functions. If I have to give a name, an algorithm for what you did heuristic search over the space of functions from names to booleans. So heuristic search, because you did not do exhaustive search, clearly, of course, I mean that's impossible. But you searched over the space of functions. And what you implemented in your mind was a learning algorithm. You were the learning algorithm in this case. Now, there's a question that comes up, which invariably comes up at all points around this time, which is this really prediction or am I just modeling data? What's the difference between machine learning and statistics? I'm not going to entirely answer that question satisfactorily at this point. I want you to keep that in mind, and those of you who have taken statistics will come back to that question maybe at the end of the semester, maybe in the last lecture, because I want you to kind of come up with an answer for that yourself before I just give you an answer. A more subtle question is, how do you know that you have to look at letters? Maybe pairs of letters will jump out. Maybe it's not the letters, maybe it is the length of the name or the first name or the last name, or maybe it is some other attribute of the name that actually is connected to the thing. How do you know that the letters are the thing that gives you the answer? And if you think that is kind of a silly question, even more tricky thing is, what are these things called vowels? How do you know that I was thinking of vowels, or whoever that made the data? It seems like, Chaim Hirsch, who made the data, was looking at vowels. And so were you. I'm sure you've never met him. You guys didn't go to the same, schools or whatever. And you seem to have brought some knowledge from home which you agree with. Now, this is a difficult thing to explain, but it's hard to quantify this, but knowledge is extremely important for designing good learning algorithms, for finding good functions. Because if you did not know what a vowel was, you would have never guessed the answer. Or maybe you would have. What you would have guessed was, if the second letter is A, or second letter is an E, or an I, or O, or U, then plus, else minus. You have discovered this concept called a vowel, but it might have taken you a little longer, because that concept did not exist. So, if you have the right background knowledge, then learning becomes faster, both for machine and human. And in some sense, this is a really, really important point. I cannot stress the importance of domain knowledge enough. Sometimes, if you know the right domain knowledge, then you solve the problem. You basically solve the problem. For instance, if you had the domain knowledge that every time Chaim Hirsch brings a data set to you, then the function is the second letter of the first name. Basically, if you knew the function, then you know the function. Then there's no learning. So, if you already know the answer, there's no learning. And that is kind of, it's important. And domain knowledge becomes really important in when you apply machine learning to, new domains like biology or stock markets and such things. You need to understand the domain. Alright, so that said, let's get started with the technical part of today's lecture, which is we're going to try to define supervised learning. When I say define, we're going to try to characterize the interesting parts of supervised learning that actually generalize between problems. Let's pretend that we have a task at hand, which is to look at news articles, and let's say you are the editor of a newspaper, and you have to look, your job is, people keep giving you news articles and for some reason you have a disorganized newspaper, they don't tell you which department they belong to, and someone gives you a news article and you have to decide whether it goes in, which section of the newspaper it goes into. Should it be sports or politics or entertainment or something? What I'm going to do in the next maybe 15 minutes is to set up, introduce some words that I'll be using throughout the semester, and hopefully you'll start using them as well. Things that need to be classified I'll be calling them instances. I'll be using the word examples for the same thing. Things that need to be classified are instances, and the classification that comes up is the label. So in this case, the classifier is a function that maps the instance space. In this case, it's a set of all newspaper articles, even the ones that have not been written yet. The set of all newspaper articles is the instance space. And the label space is the set of all labels. In this case, it's a set of all sections in the newspaper. Just to replace these pictures with some other pictures, then I'll be using the notation almost consistently throughout the semester. I'll be using X, capital X to denote the instance space, and capital Y to denote the label space. So the instance space could be things like all documents or all emails, or it could be things like days of the week, or not days of the week, just days. If you're trying to predict whether it's going to rain today or not, the instance is a day, and the label is will it rain or not. So it's a boolean. In a spam detector, for example, for a spam detector, the instances are emails, and the label is spam or not spam. And what we are going to do is hypothesize or pretend that there exists a hidden target function, a function that we do not have access to. We do not know what this function is, but we wish to get this function. We wish to find this function f. What this function does is it can take an instance x and produce a label y, but it's hidden from us. We do not have access to this function, and I'll be calling this function the target function. Sometimes I'll be calling it the oracle, sometimes I'll call it nature. It's a function that we do not have access to, but can actually be applied in nature. And in this scenario, I can think of learning as a job of learning is to find this target function. It's search over functions. This can be defined mathematically as well, and in fact, if you look at books and like for example, if you look at the textbook that is not required but recommended, Tom Mitchell's book, this is how he frames it. Learning is a problem of search over functions. But how do you search over functions? And that's what you guys did when you were looking for these, the badges function. The problem, the search over, how do you guide the search over functions? That's the algorithm that does the search, by the way, is called the learning algorithm. And how do you guide the learning algorithm? Because the learning algorithm cannot see the target function, because if it can see the target function, problem solved. The learning algorithm cannot see the function, but it can see the function in action. There are some instances x, let's call it, for example, x1 here is labeled with f of x1 by this oracle, by nature. So the learning algorithm does not have access to this function, but it has access to this function in action. It can see examples where this function has been applied. And in this picture here, I have got n examples. So there is a set of instances that have been labeled by the target function. This set, we'll be calling it the training set. And the learning algorithm, what it does is it takes the training set and does something inside the black box or the blue box and spits out a learned function. Here I'm calling it g, and what g does is it is also another function that looks just like f. It has the same signature as f. It takes instances and produces labels. So it's a function from x to y. Questions so far? And feel free to ask questions and also tell me if I'm going too fast or too slow, or if you wish I had been talking about something else. Yes?
So the target function is the perfect function.
The target function is the perfect function. The perfect function, to noise. I mean, sometimes there is noise that you cannot control for. Maybe even the target function might be noisy. But it's the hidden, it's the thing that we do not have access to. Yes. Yes?
The x's are training data, not the f of x.
No, the x's and the f of x's together form these are pairs, x, f of x. And in subsequent lectures, I'll be calling it x, y, because y is a label for x. So xi, yi will be the training data. We will see a fixed set of it. And in fact, this kind of labeled data is going to be the most precious resource when it comes to machine learning, because often it becomes expensive to get this training data. Yes?
So if I give you a label, can you give me like examples where you did the label?
Give me an example. Can you?
So let's say you say spam and you will give somehow can figure out.
So when you say spam, you want me to generate a spam email.
Yeah.
That kind of a classifier, there exists a kind of oh man, I can't use the word that I'll be introducing in the next 5 minutes. But there's a version of machine learning called generative learning, where you will generate examples, and then in this very curious way, you will pretend that you will generate examples, and then apply this process in reverse to generate the label. We will be seeing a generative, at least one generative model, namely the naive Bayes classifier, about 2/3 of the way into the semester. Other questions? Yes?
So can G be same as F, or it will be close to F?
One hopes that it's identical, but in practice, in anything but a toy problem, it won't be identical. And hold on to that thought, and I'm going to make a curious argument in about 20 minutes that will say that G can never be F. A question that I want you to think about, maybe not answer, but because the answer is already in the last lecture's slide, is this is not the only training protocol. Here I am making strong assumptions about the nature of input that the learning algorithm gets. This is the supervised learning protocol, and I want you to think about, in this language, as an exercise, I want you to think about the other protocols for learning, how they would look like. Unsupervised and active and such things. If you have questions, think about it and come back with questions in the next lecture. Alright, so let's say you've done some learning, or let's say the learning algorithm has finished learning, and we have a target, we have a learned function G. Of course, we don't have a target function F. But how do you know that this function is good? And that's related to the question that you asked. And one way of checking is, say, the instance space is a set, right? You can always ask for more examples. Not always, sometimes. You can ask for more examples. Basically, pull out a new email and apply F on it. But we don't have access to F, but we can probably, if we are in a lucky situation, we can ask for F to be applied on a new example. We have G, so we run G on that same example and check, are they different? If the learned example is different, if the learned, classifier makes a different prediction from the oracle, then we know that we made a mistake. And we can ask for the expected error in this sense, and that could be a measure of goodness of the classifier. So in practice, instead of expectation, what we can do is just repeat this process on multiple test examples and calculate the average error. Yes?
So I guess how would you, I don't know, let's not talk about, how would you handle the case though of like the spam? Because you obviously pretty much usually know with 100% certainty, if something is labeled as spam, that it is spam.
When you
But
say
the
you,
reverse is not necessarily.
no, hold on. When you say you will obviously know with certainty, you mean me or a classifier?
I guess even you could say the Oracle, which maybe Google is the user.
No, the Oracle is not Google. The Oracle here is the user. Who's,
Or the user, the person who goes and marks it.
yes.
I mean, usually I guess you would know, with almost 100%
Sure.
certainty if it's marked as spam, then it is spam. But you don't really necessarily know that the opposite is the case. How do you...
That's right. And in fact, in most situations, the Oracle is going to be noisy. In fact, the Oracle or the teacher or whatever you want, nature or whatever you want to call it, does not know everything. And that's again a fact of life as well. All you can hope for is to be at least as good as your teacher, as the Oracle. But there will be noise. In some situations, actually, the instances just cannot be classified because I have had at least one email where I was never sure whether it's spam or not. Right? I mean, it could happen. So, you're right. I mean, the Oracle need not be perfect. And in fact, the Oracle almost definitely will have noise. Sometimes we can kind of mathematically account for that, and we will eventually account for the fact that the Oracle might also be noisy. So, going back to knowing how good you are, or how good the learn function is, what you do is you take the classifier, apply it on a bunch of test examples, and check whether you got the same, whether the prediction agrees with the ground truth. Sometimes the ground truth is also called the gold standard label. So you check whether the prediction agrees with the gold standard, and if it does, you get a point. If not, you don't get the point, and you add up the number of points you get, and that's how good your classifier is. Question. And this is something that's important. Wait, hold on. I see a hand.
That was my question.
That's your question. Okay, then that's a question to the class.
No.
Who says no? I see many hands jumping up. So you've spoken before. I've never heard your voice. Yes.
There is a 10% rule, isn't there?
There is no 10% rule. What's the 10% rule?
Like you use the 10% of the training data as your test data.
Why not 11?
That's like.
I personally use 2/3 or 1/3. Depend. Or sometimes I use 25%. Sometimes I use. Sometimes you don't even have you don't even get to control it because somebody else does the split screen. But the question still remains.
So it can't be used as.
No, you can technically just take the data, put it in, and then you get 100% on the test data because you've already seen it. So you had a hand to this stuff.
Yep, so how do you evaluate if you use testing them?
Okay, so that's one problem.
And overfitting then,
You're using a word that I don't know what that is.
okay. So the example we want to test upon, if we fail upon them, then how will we test?
It's almost a philosophical question. Yes.
I think that you can, you can't necessarily at each, perhaps iteration use test data, but you can effectively use, test examples and your training data and use your full data set. You just can't use it all at once. So maybe you might have an algorithm that has a bunch of parameters to it or something. Maybe you can iterate and use different examples each time.
I actually don't agree with that point, but I will tell you in a minute why I don't agree. One more answer and then I'll get to you in a minute.
So if you use test data for learning, it will be like cheating.
Okay, you've probably seen what I'm going to say. That's the point. I was going to say that I'm going to be harsh about using test data while training and call it cheating. The reason is the test data represents a way of evaluating your classifier. Think of test examples as looking at the future, because the point of learning the classifier is to make predictions in the future, and what you want to do with the test data is to know how good you will be in the future. And if you are looking at the test data while training, you are effectively asking for a peek into the future. You do not have access to the future, so you cannot look at the test. That's like a vague argument, but the more concrete thing is, here's what I will do. Here's what I guarantee I will do if I'm allowed to look at the test set. I will use the training set to learn a classifier, and if I know that I'm going to be evaluated in it, I'm going to put all the test examples in a database, not learn, just put it in a database, remember it, and then when I'm tested, I'll throw out my training data, just remember the test set, example comes in, I'll look up the answer. 100% classified. So, I will not learn, I will force myself not to learn if I know that I'm going to be tested only on this. And that beats the purpose because I have not generalized. Learning is generalization. Looking at the test set affords the ability to not generalize. By just remembering examples, remembering the labeled examples, and remembering is not generalization. If I want to, the reason I'm kind of stressing this point is because you will come to a point where when you apply machine learning, where you will be tempted to look at a test example. It might be something that, it's like the deadline's coming up, you need to get the product out in 15 minutes, and you're stuck. You need to get the damn classifier to work. You don't know how to make it work. You need to tell your boss or whatever, someone who's higher up, that your classifier is good, and you set aside some test set and you're constantly beating your head against the wall to make the numbers on the test set look good. It's so tempting to look at the test set. And in fact, what I tell my students when we are applying machine learning is don't even look at the test set. And because information might leak from the test set through my head into my classifier. Don't even look at the test set. I usually zip the file, put it aside and unzip it like once or twice, and then delete the thing. Okay? It might seem a little hard line, but it's very, very tempting to look at the test set. End of the day, you'll ship a product or you write a paper making a claim using this model of testing. That is not true. You will claim that your classifier might end up being better. There are certain very, very, very limited situations where the test set might be looked at, but I'll probably get to that much, much later in the semester. Yes?
If you're trying to learn through noise, wouldn't seeing the test set help you learn, because then you can still get one of the test examples wrong?
Yeah, but the test example is coming from the future. I do not know what spam emails will look like in the future. So if I want to know how good my spam email detector is on detecting spam, there's no point in my saying that it is good after having looked at an example. If I have seen the label, then I have the label. I'm not making a prediction. The hope is, in fact, the whole point of this class, of the algorithms that we'll see, is how well can we learn despite noise. Noise is going to be our constant enemy, and we have to somehow get around it. Sometimes we can't. In fact, sometimes the noise can be so high that the signal to noise will be extremely unfavorable, in which case learning cannot happen. But even in that case, you should not look at the test set, because a test example is from the future. Did I see a hand up? Yes.
I'm not clear about the labeled training data and the test set, because labeled training data, in very simple words, can I say it's just a set of the given input and the output, and then you come up with a function which is called a classifier, right?
Yes. Yes.
And then how is it different from the test data?
The test set looks exactly like the training set, except it's a collection of examples that your classifier has not seen, your learning algorithm has not seen. It's a collection of examples that were not available during learning and will be used for evaluating the classifier that the learning algorithm produces. Yes?
I don't know, to kind of play the devil's advocate a little bit though, couldn't you, according to your rules, you can really only even use the test data once, otherwise you use the test data in training.
That's
Because
right.
if you go,
That's right.
a computer scientist go and try and do this and you say, oh, it's only matching the test data some sort of percent, let me change these parameters, you're really doing machine, you're doing learning.
Yeah, you're learning on the test set.
Computer.
You are learning on the test set. And the human is now part of the learning algorithm in the protocol that you described. And in fact, some of you may have heard me say this, the most popular learning algorithm is graduate student descent, where the student is part of the algorithm and kind of tweaks the whole thing again and again till everything works. And that's how some papers get published. Alright, let's move on. I hope this point is clear. Last question.
I have a question. So is it like if my training set is very large, or the larger I get, the closer my function G will get to the target
Yes,
function?
in general, that's right. Yes. And in fact, we'll make that then formally mathematically.
So you're saying you can never have continuous learning?
You can. You can, of course you can have continuous learning. In fact, one of the coolest projects I've seen is something called never-ending learning. A classifier is out in the wild and constantly learning somehow. But even the problem with that is evaluating how good the classifier is, and that becomes pretty tricky, and you have to play some pretty nifty games to evaluate that classifier. Alright, let's move on. So let me just quickly summarize what we have, and I'll introduce at least one new phrase here. So the setting for supervised learning is given a training set, a collection of examples of the form x and f of x, or x and y, where f is the unknown function that we wish to approximate. And typically, the example, the input x, is represented as a feature, in a feature space, as a feature vector. And when I say feature, think of it as a collection of attributes that describes the example. So an example of a feature for the badges game could be, is the first letter a vowel or not? Is the second letter a vowel or not? Is the third letter a vowel or not? You don't know which of these features is relevant, so you try to add a whole bunch of attributes and you stack them up and you call it a vector. And the feature could be a vector in the space of 0, 1 in the Boolean hypercube. So this is how I will represent the Boolean hypercube. It's a set of all vectors, n-dimensional vectors, that consist of only zeros or ones. The feature vector could be an n-dimensional real valued vector, the vectors that you all know and love. And this mapping from instances like emails or names or photographs to the feature space is often a deterministic mapping. It's a fixed function that is given to you, or if you are building a classifier, this is the place where you will be most creative. You could ask questions like, for the names, the badges thing, you could have said, instead of asking vowels or classifiers, you could have asked, is the second letter in the first half of the alphabet or the second? Is the third letter a digit or not? I'm not sure anyone's name has digits, but you could try. And things like that. So, sometimes you have the flexibility of deciding the feature space. And there you get to be creative. That's where domain knowledge often gets thrown in. And sometimes, very often in fact, if you get the right features, learning is almost trivial. If you get the wrong features, learning becomes very difficult. In most of the initial parts of the assignment, the class assignments that we'll see in the initial parts of the semester, I'll give you feature functions. I'll give you featureized data. As maybe we go along, I'll ask you to play with some features and try to come up with some. Or maybe I'll actually have you build features even in the first homework. By the way, the first homework will be released next week, just FYI. In any case, so you have a feature, you have an example x, and that example has a deterministic mapping to a feature vector. So sometimes I'll just be saying the training example is a feature, is a vector. And f of x is the label. And our goal is to find a function that looks like f, a good approximation for f. And the label, the kind of label that the problem has, decides what kind of problem we have. If the label can only take two values, then we call it binary classification. And I'll be using -1 or +1 for positive and negative examples. Sometimes I'll be using 0 and 1 for positive and negative and positive examples. So zeros are negatives and ones are positive. You could be using spam and not spam if you want. So if there are two labels, then it's binary classification. If you have a finite set of labels, like the categories in the newspaper, like sports, politics, entertainment, and if it's more than two, it's typically called multi-class classification, where the number of classes is more than two. If the output space, if the label space is all possible real numbers, then this problem is called regression. Some of you may have seen regression before. It all falls in the same general framework. Alright, so any questions about this?
What is the use of feature space?
Features are, there's a subtle difference between instances and features. Instances are objects in the real world, like emails or photographs. Features are how these are represented for the learning problem. These are the attributes that represent the instances. So, if you come from an ECE kind of a background, think of features as being the outputs of sensors. So you deploy a collection of sensors on the instance and you use the sensor readings to kind of describe the input. And the classifier is a function that operates on this feature vector, not on the input directly, because the inputs are objects, not vectors.
So, in an email, what would be an example?
In an email, in fact, I was going to ask you to brainstorm features. Probably that might even be the one of the slides coming up. But so, what would be interesting email features for a spam email?
Subject line.
But I want something that's mathematical. So,
Number of spelling errors.
number of spelling errors,
Exclamation point.
number of exclamation points.
Yeah, I was gonna say different kinds of exclamation point or number sign.
Yeah, or just the words in the email. Is the word free prominently featured in the email?
I have a question rather than an example. So does the mapping have to be deterministic?
You know, that's a good question. For nearly everything that we talk about in the semester, I'm going to assume it's deterministic, but a really hot area of research is how do you learn this mapping?
Because you might have like 30% of your users that might really like free offers and always click on them, and they don't consider that spam.
No, they don't. And what happens is you are learning a spam detector. So you're not going to, a feature is just, as a designer of this system, you're only offering the learning algorithm the ability to look at this sensor reading. The learning algorithm can then decide this is not an important feature. It can downweight this feature or discard it if necessary. And in fact, one way of thinking about learning algorithms is it's a device that looks at a feature representation and decides how important each feature is and then builds a function out of the important ones. Good question. Yes?
Could you explain the difference again between regression and the multi-class?
Regression is, the output is all real numbers.
All real, okay.
And in multi-class, it's a finite set.
Okay.
You have k categories to put.
Definitive set of discrete numbers.
Buckets.
Okay.
You have buckets. It doesn't have to be numbers. It could be A, B, C, D. Sports, not sports, sports, entertainment, and politics, for example.
Okay.
Yes.
So I guess another class criteria you can use would be like IP address as well as a set of.
Yeah, you could for the spam thing.
Yeah.
Yes. In fact, I bet they do. I bet there are IP addresses that are spammy. Alright, so let's just step back a bit and look at the kind of applications where this sort of where machine learning in general is useful. I can think of three situations. One, there is no human expert. We are trying to discover knowledge here. And this kind of thing often shows up in biology. I want to identify DNA binding sites. I'm not sure what that means, but I'm told that phrase makes sense. Sometimes there could be a situation where the human performs a task, but it's not clear how they do it. If I show you a photograph and you tell me that there's a cat in the photograph and I ask you why, it's not often clear. You'll tell me because there's a cat in the photograph. But looking at the pixels, how do you know that these combination of colors form a cat? You can make a judgment, but you're not sure why. And in that case, you are the oracle. You are the target function that the learner tries to approximate. Sometimes the desired function is easy to observe, but not easy to obtain in closed form. Is the stock price going to go up or down tomorrow? All I have to do to get another labeled example is to wait till tomorrow. And then I get another example. And I can keep waiting and I can keep collecting data. But I don't know what the function is because And specifically, just a few examples of where binary class. Yes.
And previous slide, how are these supervised learning like?
Oh, these are not necessarily supervised. The stock market thing is supervised in the sense if I wait tomorrow, I get another training example. The objects, the humans performing a task is supervised because I can have a bunch of people label cats. The first one is difficult because there is, in order to get supervised data, you have to do wet lab experiments. You go to the lab, run a bunch of things, fill, I don't know, test tubes and stuff, and you get one data point. So in that case, there may be a human expert, but it's extremely expensive to get data. And even the human expert may not be entirely sure what's the right answer. So just as an example of spam filtering, I have a few slides of this. You can look at it later. I'm just going to list a few. Of binary classification. Spam filtering is clearly binary classification, and email is spam or not spam. Recommender systems can be framed as binary classification. If you like this movie, will you like this movie? Yes or no? A place where binary classification is getting more and more important is in malware detection, in places like the App Store, where you can ask whether this app is spam or not spam. Time series prediction, will the stock price go up or down? Time series is technically regression, right? Because I can ask, what will the stock price be? But if I don't care about the value, I only care about the direction, I can frame it as binary classification. So the point is, many problems can be shoehorned into this setting of binary classification. You can force problems to look like binary classification. And there are a few other examples, maybe it's not here. So today, I want to talk about what are the different things that we need to be able to decide for supervised classification, in particular for binary classification. My hope is, so how long does this class go? It goes on till, so we have half an hour. Yeah.
So like you had the example with the sports and stuff. Could I just
one of the most awesome papers I've read in machine learning was from about 15 years ago now, is how do you reduce multi-class classification into a series of binary classification? So if I want to decide whether something is sports or, politics or entertainment, let's say you have 3 categories. It is multi-class classification, but I can have a binary classifier sitting inside that says, is it sports or not sports? Is it entertainment or not entertainment? And is it the other thing and not the other thing? And somehow put these decisions together. So many problems can be reduced to my binary classification, which is why we'll be spending a good chunk of this semester studying the guts of binary classification.
So what problems can
regression?
Oh, I mean from the multi-class.
Multi-class can formally be reduced to binary classification. It's not like you do it for free, you give up something in exchange. I hope we'll have a lecture on multi-class. If not, you can come and talk to me afterwards. After we do, linear classifiers and stuff. So when it comes to supervised learning, we need to be able to decide 5 things. I hope to cover the first 2 today, the third one in the next lecture, and 4th and 5th over the rest of the semester. 5 things are, we need to decide what is our instance space, because if you don't know what you have to classify, how can you build a classifier? These are the inputs, and as part of this instance space determination, we also have to decide what are the features. Sometimes the features are given to us, sometimes you have to play with them. You need to decide what's the label space. Once again, sometimes this judgment is made for you because it's binary classification. The labels are decided. It's true or false. Sometimes the labels are decided to you by your application. But you need to identify it. One of the most important things that you need to be able to decide is what is the hypothesis space. This is the search space that your learning algorithm operates on. This is the space of functions that your learning algorithm explores. And we'll touch upon that briefly. We need to, of course, decide what's the learning algorithm. And we need to know what is success. How do you know that a classifier is good or bad? And this is the evaluation metric, and eventually we'll be referring to this as the loss function, because we'll decide what is loss instead of what is success and try to minimize it.
The hypothesis space is sort of limited by what features you're looking at.
Yes, most definitely yes. The hypothesis space is determined by the features, because those are the functions that we'll be, the functions that we are learning are functions from the feature space to the label space, because the instances the instances are just real world objects. So let's look at these in order. Let's talk about the instance space. So this is the picture I had earlier, where you have instances that are mapped to labels by functions. And let's focus a bit on the instance space, or the feature space. I said before, I'm going to repeat it because it's important. Designing a good feature representation is crucial and often makes or breaks the success of your classifier. And in some sense, the instances are defined by the features. And we looked at a couple of examples, so I'm not going to stress on this. And this was what I was going to say. We brainstormed some features for email spam. I was going to ask you to brainstorm features for the badges game. Can someone tell me a feature for the badges game that we have not touched upon before, and someone who's not spoken before? You've spoken before.
Yeah. If the tongue touches the top of the mouth when speaking the name.
Whoa, that is so cool. I'm going to repeat it because this is the first time I've heard that feature being proposed. If the tongue touches the top of your mouth when speaking the name. Now that is so awesome because the sensor that is required to produce this feature is a tongue. Right? But it's a Boolean feature.
It will not or it will.
Huh?
It will not or it will.
It will not or it will. That's right. That's it. I think we can't do better than that, so let's move ahead. So, I do want to point out that deciding a feature representation is not learning yet, because we are talking about deterministic functions, fixed functions, like the tongue function. It's fixed, it's not learned, the learning algorithm does not know, does not care often what your feature representation is. It's just a function that maps inputs like names and emails to vectors. And I've stressed this enough, it's an important aspect of, it's an important design choice that you have while making the whole system work. I saw half a hand. No, good. Alright. You should be comfortable with the phrase n-dimensional feature space or n-dimensional vectors, because we'll be I'll be talking about that a lot. You will be implementing n-dimensional vectors when you're implementing learning algorithms. And in fact, given that every input example, every instance is deterministically mapped to a feature vector, for pretty much the rest of the semester, I will be talking about inputs being the x's being feature vectors. The instance space, as far as I'm concerned for most of the semester, is the feature space. Because this mapping was done yesterday, it is fixed, and we no longer care. Unless we care about, unless we want to think of the features as being the game we want to play. Yes?
So does that mean you have to choose either all binary features or all binary?
No, you don't. Because invariably, once we come to linear classifiers, we'll be treating binary as just the number 0 or the number 1. So the binary features are embedded in the real value space.
But you can have some of your features are
You could.
ones on the new value.
Yes, and in fact, the scaling issues often crop up, and these are the dirty things that people don't often talk about when we are talking about the clean formulations of learning. But yes, we'll end up letting these different kinds of objects live in the same space. If you are uncomfortable with the idea of vectors and spaces, this is a drawing that's supposed to remind you. You have a vector that, this is a two-dimensional, a vector is just a point in an n-dimensional, in some space. In this case, it's a two-dimensional space. So this is the point x1, x2. I saw.
So properly speaking, it's the x's as represented by a feature vector that constitute part of the training data. So you don't have you don't have training data until you have your instances represented by it.
Actually, no. So you have your training data. So it depends on where in the pipeline you're sitting. So if you care about making the system work, then you are going to look at training data as instances. But if I care about analyzing learning algorithms and designing learning algorithms that are independent of the problem, then it's convenient for me to pretend that feature extraction has been done and come to this mathematically clean and unifying way of thinking about it. But feature extraction, I cannot stress, is important, and feature design and exploring the set of feature functions is often what will end up making your classifier work. So just to tell you how things like the second letter, so you could have a feature that says, I want a sensor that looks at the second letter and produces a feature that's the second letter. How the hell does that become a vector? The second letter is one of 26 things, A through Z. Often we have to come up with encodings that take these discrete objects like letters and put them in vector spaces. So here I have a bunch of names, and the feature extractor or the sensor that we are looking at is going over the name and looking at the second letter here. What we'll do is map the second letter into a vector. Here it's every time it's an A, this bit becomes set and everything else is not set. For a B, I have decided that this bit is set and everything else is not set, and so on. So how big will this vector be? 26.
We don't know.
Huh?
Chinese letters.
Yeah, sure. But the thing is, you create a vector space where it's one dimension per letter. Sometimes your feature vector could be a feature could just be a number. If I say something like the length of the name. And I could have a feature vector that's the second letter of the name and the length of the name. So that's like a 27-dimensional vector that basically pads this vector with this number. So you get a vector that looks like this. 1 followed by 25 zeros and the number 5. So this is in R27. The reason I feel like I'm going a little slow. I see a lot of heads nodding, but I am more worried about the heads that are not nodding. If you're not comfortable with the idea of high-dimensional vector spaces, you need to stare at it, and you'll get used to it, not necessarily comfortable. Yes.
These are actually two features, but the first feature is the vector, and the second feature is so you're.
It's a scalar, but a scalar is a very small vector. It's a one-dimensional vector.
Yeah, you combine the vector with the scalar.
I'm just padding them up. I'm creating vectors at the end. Most of the time, you'll end up only working with these vectors.
Why do we need a 26-dimensional? Maybe we can have like a binary translation.
Oh, this is a question I always get. It's a great question. It means you've been thinking about this, but you've thought a little too much. Think about what these vectors represent. So let me ask the question back to the class. Why do you need these 26-dimensional vectors? We know that the 26 dimensions can be encoded more efficiently with log 26 bits, right? I can say that A, for example, I can say that A is the is 5 zeros. B is 00001. C is 00010, and so on. So this is my 5-dimensional. This is A, this is a B, a C is, and so on. The problem with this encoding, even though it's correct, is it introduces artificial similarities. it now tells me that a D, which is in this encoding will be 0, 0, is 1 bit away from a B, but it's 2 bit away from an A. You're introducing some artificial similarities between these dimensions, between feature values, which did not exist in the original problem. Yes?
Then why don't you use 1 to 26 in scalars?
Why don't I use 1 to 26? Again, the same problem. So if A is a 1, B is a 2, and C is a 3, that means, C is a 3, that means C is closer to B than A. In a certain way of thinking it is, but maybe it's not. So I'm not saying it's wrong, but it introduces, you're making an assumption. Every time you introduce a feature, you encode some features, you make assumptions.
But those assumptions could be true, right?
Oh, it could. I'm not saying it can't.
Representing this, you are assuming that all of them are independent of each other.
Yes, you're right. And in fact, I'm not even claiming this is the only right way of doing it. You might need to make that assumption because, for example, if the correct classifier is this in the first half of the alphabet or not? Or is the second, you could come up with functions that are dependent on a particular encoding. In which case, the other encoding will fail. And that's why feature engineering is an art. Last question because I want to move ahead.
Okay, sorry. So I was just wondering, I guess, when you have more challenging, like how would you encode things when you have, like, start having stuff data that has a lot of structure, but it doesn't necessarily fit into like a nice, neat little pretty vector model? I guess what kind of techniques do you usually use?
You can always fit things into vector models.
What?
You can always think, by these kinds of encodings, you can always make things vectors.
Well, I guess I was going to say, like, maybe if we were going to encode like a chess, like a whole chess game where you have
a chess board.
Or not even a chess board, but like a whole chess game. If you want to start analyzing that for some reason, like how would you encode that where it has like time and it has all of these different features without introducing?
You know, I'm not going to answer that question because I want you to think about it. All I'm going to tell you is there exist ways of doing it. Think about it and come back to me with an answer. I know you can find it because it's a very obvious answer. But if you see the answer, you'll be like, really? But there is an obvious answer if you allow the dimensionality to be arbitrarily large. And that's the clue I'm going to give you. And think about it. I'm going to move ahead. I saw another hand. You can, unless it's a 30-second question, I'm not going to take it.
So the feature engineering assumptions, so are they part of the hypothesis?
It's not. It's the hypothesis class does not. It comes after.
So if you're taking assumptions, so I mean the domain knowledge comes in the picture. Right?
Yes.
So I mean the hypothesis is not related to it.
We'll come to that once I tell you what a hypothesis is. Right. So good features are essential. I've stressed upon this a lot. It's very easy to come up with bad features. I have a great example here for the badges game. Is there a day of the week that begins with the last letter of the first name? If there is, then the label is plus, otherwise the label is minus. Maybe that's the right classifier. Maybe that is the right classifier, but the fact that at least some of you are laughing suggests to me that there's something weird about that feature. It's possible this could be the right feature, but complex features often end up being problematic. A lot of effort goes into designing features, and like I said, it's an art and it's not something that I can necessarily teach, but we'll look at some general principles for deciding what might or might not be good features as we go through this class. So that's all I have to say about instance spaces, the instance space. Let's look at the label space now. The label space is the output of the classifier. And the label space decides what kind of problem we have. If the label space is a finite set, we call it classification. Binary classification, the label space has two elements. Multi-class has two possible labels. If the label space is a countable set, namely a set of all possible graphs, for example, that is called structured prediction. And just as an advertisement, I'll be teaching a class on structured prediction next semester. In this class, we'll primarily be looking at classification. But there's also, if the label space is real valued, then you are in the world of regression. We'll be looking at least one, some of you have seen linear regression, we'll be looking at linear regression at least to some extent, maybe in a few weeks. The labels could be a ranking. Like for example in Yelp, the star rating is actually a ranking. There's an ordering between the labels. There are 5 labels, so it looks like multi-class classification, like 5 stars. But a 1 star is closer to a 2 star than a 5 star. So there's an ordering in the ranking, and so these are the labels are ordered, and that's called a ranking problem. There's not much else to say about labels really. We'll be looking at classification for most of the semester with a little bit of regression. The most important thing here is called the hypothesis space. Remember that learning is a search over functions. If you are searching, you need to define the space that you will be searching over, and that space is called the hypothesis space. I'll be using this phrase hypothesis space a lot. Most of our analysis of machine learning will be analysis of hypothesis spaces. And the reason hypothesis spaces are important is because of a weird claim I'm going to make right now. Machine learning is fundamentally ill-defined. Let me try to convince you that machine learning is impossible. Let's take this data set here. You have 4-dimensional inputs, x1, x2, x3, x4. They're all Boolean. And I'm giving you a training set with 7 examples. And I want you to stare at this data and tell me, find the function. It's a Boolean function. And here I'm following a convention that I'll be using almost through the rest of the semester. The zeros represent false and 1 represents true.
Is it okay to use K-maps?
Use whatever you want. Who said that?
There's not enough data to design one function.
Excellent point. Why?
Because there's 4 variables, you have 2 to the power of how many functions there are? Functions there, and without that you cannot really decide on one.
Okay, that's a very good point. Can someone else pick up on that thread or? Yes.
So I guess I don't know. Maybe it's like elaborating a bit, but because you need to see, I guess, the entire possible space of inputs and see the output in order to uniquely identify a particular.
How many functions are there?
Because there are, you have how many functions, however many inputs you have to however many outputs. It's the number of inputs in your input space times the number of outputs in your output space multiplied together, and that's how many possible functions you have. So you need to have enough data to identify it.
I think your counting argument is not accurate, but the point that you make is correct. The point that both of you make is correct. Does anyone else have something else to say about this? Can you learn a function? Yes.
So the number of functions will be 2 to the power 4.
Yes.
So for that the data set is apparently very less.
So let me give you, let's say that you have learned a function. Let's pretend that the oracle is adversarial. That nature, for whatever reason, is conspiring against you. And let's say you have learned a function here. Let's say you think you've learned a function that agrees with all these 7 examples. And now, when I'm testing, I'm going to ask you, what is the label? Let's pretend that I am nature here. I'm going to ask you, what is the label for this one? And let's say the function that you learned predicts that the label for this example is a 0. Because I'm adversarial, at that point, I will tell you, oh no, the label is a 1. And now you go back and you will learn a function again, using this now extra example. And you learn a function, and now I'm going to test you. And at test time, I'll ask you, what's the label for, let's see what's not here, 0, 1, 0, 1. And the new function that you learn.
Already, it's the bottom one.
It's the bottom one? Okay. So let's say it is 1101. Is that there? Good. So I'll ask you what's the label for 1101, and the new function that you've learned, accounting for this extra example, let's say that function says this label is a 1. And of course I'm an adversary, I'll tell you, no, you've made a mistake, it's a 0. And I'll keep doing that till you force me to reveal every possible row in this table. And there are 16 rows in this table because there are 4 bits. And at that point there's no more learning, because I have revealed every possible example that can exist. There's no possible generalization. There are 16 rows, and I've taken the pain to write down all the 16 possible inputs. There are 16 rows here, and I have shown you only 7 of them. There are all these other rows that are not in your training set, and how many functions are there? And this is a kind of counting argument that you should start getting comfortable with. How many functions are there? Think of the outputs as there are 16 possible, there are 16 inputs, so there are 16 outputs, and each output can be a 0 or a 1. There are 2 values that each output can take. And every assignment of these values is a different function. So you can have a function that is all zeros. And you can have a function that is all zeros except for the last one. And so on. There are 16 possible outputs, and each assignment to these outputs is a different function. So there are 2 power 16 functions. And every different way of filling this slot is a different function. There are so many functions. I have only shown you 7 of them. And every time you come up with a function that agrees with these 7, I will tell you that you are wrong, because I will adversarially pick a row that does not agree with your function. Is this argument clear? This is an important point. I see half a hand.
This is more of a philosophical question, but isn't human learning also like that? Like you always see
This is human, machine, everything. This is a mathematical argument. Yes. So I'm arguing that learning is impossible. How could you possibly learn anything? Now, I mean, if the answer here was, no, you can't learn anything, the rest of your semester is free. So, what gives? What's going on here?
you can't learn everything, but you can learn something from what you have. So
no, but I can't learn anything from what I have.
You can learn something. Like your answer will be correct for the first 7 spaces.
No, I want exact learning. I don't want an approximate function. In this case, I want the function, not a function that agrees 15 out of 16 times.
I think it's kind of like, you might not be able to know for sure, but you can make probabilistic arguments, and you can say, okay, I might not know what this function is, but this is pretty good, and this
no, but I don't want pretty good, I want exact, at least for now. At least for today's lecture, I want exact. And I want to hear somebody who's never spoken before. I feel like these 4 people are talking a lot. So, yes?
Doesn't that assume that all the outputs have the same probability of being the correct output?
For now, let's pretend that it does.
So, okay, so if all the, well, never mind then.
So, can you tell me an answer that assumes, so I'm trying to be, necessarily adversarial here. So, how will you beat me?
Get you to reveal all the rows.
Sorry?
Get you to reveal all the rows.
Okay, that's okay for a 4-dimensional input. I work in natural language processing. Routinely, the dimensionality of my input is roughly about 500,000. 2 power 500,000 is hopeless.
You can add the oracle as a feature, and
you don't have access to the oracle.
So, like say for example, whatever your algorithm predicts, you give out the answer as the opposite. So
no, then I know that you're playing that game, and I will give you the answer that is. I'll flip the bit before I give you the answer. See, the thing is, I can be arbitrarily adversarial. Nature can be arbitrarily adversarial, and the question is, how do you get around that problem?
You do know, I mean, you are learning for sure what things aren't the functions. I mean, doesn't that get you closer?
It gets you closer, but not there. the problem is, in the land of 2 power 500 functions, getting closer is getting nowhere. So, remember, learning is a search over the space of functions. The space of functions. The answer to most things when you are faced with a problem in theory or mathematics is make an assumption. So what we do is we make an assumption. You, in this case, could make an assumption that the adversarial oracle is not operating on the space of all possible Boolean functions, but some restricted subset. How do you know that restricted subset? You make a guess and hope it's right. That's pretty much often the best we can do. The hypothesis space, remember, is a set of all functions that the learning algorithm operates over. It's not a set of all possible functions. And one of the most important things that you can learn in this class, in this lecture at least, is if you're looking at the space of all possible functions that can exist, learning is definitely impossible, because you will meet an adversary that will fool you. Instead, if you choose a hypothesis space that is smaller, then you have probably a better chance of getting a function that agrees, because it's possible that you will not find a function at all. It's possible that the choice of your hypothesis space is wrong. And that's a design choice again. That's the second design choice you have to make. The first one being features. The second one being, what hypothesis space do I let my learning algorithm explore? Let me give an example of a hypothesis space for this thing, and that will be the last thing I'll do. One class of functions is a set of simple conjunctions. What I call simple conjunctions are simply Boolean ands between these variables, and I do not allow for negations. So you have 16 possible conjunctions, and let me give you an example. Let's say this is x3 and x4. This is a function that returns true when x3 and x4 are true, and returns false in all other cases. So for example, for an input like say 1, 0, 1, 1, this function will predict 1. Okay? The reason I have 4 bits here is because I could write down all possible simple conjunctions. This is another simple conjunction that says false. I don't care what the input is, the output is 0. It's a conjunction of nothing. This is a conjunction that of a single element, it says the output is x2. What if I restrict myself to only this hypothesis space? Is there a function that agrees with these 7 examples and is from this set? Can you find a counter example, for instance, for this function, x3 and x4? The fourth row, that's right. How likely am I to recommend Windows 10? Good time to ask the question. So, this row here, according to the function, it looks at x3 and x4, and the function x3 and x4 should say 1 only if both of them are 1, but the output, the oracle says 1 when only one, when it's not, that condition clearly doesn't work. So that's a counter example to that function. As a exercise, I want you to think about how many simple conjunctions are there when there are n inputs instead of 4. It's very similar to a question that is in one of the quizzes, and I'm just feeding this question because we'll be asking these kinds of questions a lot later. You don't have to tell me now, tell me later. But I'm going to argue that for every element of this set, there's a counterexample. You can verify this later. There is no function in this hypothesis space that fits this data set, which means if I let my learning algorithm explore this hypothesis space, it will come back and tell me there is no function. So what I have done is I have chosen a hypothesis space that's so small that learning fails, which means my choice of hypothesis functions was incorrect. I'll start the next lecture by showing a hypothesis space where it succeeds. In fact, I can show you the hypothesis space right now. It's this class of functions called M of n rows, which looks like this. You pick n variables, a particular set of 3 variables, and I say that there is at least 2 of them should be true. If at least 2 of them are true, then the output should be 1. Otherwise, the output should be 0. And I'm telling you up front that there is an M of n rule that fits with these 7 examples. And we'll continue with the philosophical question of so what when we come to the next class. Alright, just a quick reminder of announcements. If you've not signed the academic integrity policy of the School of Computing, please do it and return it to the front desk. Please complete the survey if you have time. I would really appreciate it. Also, the quiz is due next Tuesday, so please finish it. Tuesday or Monday, whatever day it says.